I welcome you all in this lecture on state variable formulation, which is a sub course for a sub module for course on modeling and simulation of dynamic system, which you are going through. State variable formulation is actually a way of representing the system equations and that is the equations of any dynamic systems. So, till now in our some of the earlier classes we have seen the transfer function approach for finding out a relation between output and input, but the transfer function approach has got certain limitations. Okay. It is done in the complex domain. Transfer function approach works out in the complex domain, and there are many more limitations, but coming back to the modern approach, that is if we talk about say modern control systems, where essentially we want to see the variation of the things with respect to time. Okay. So, there this state space approach is very much used. So, as we have seen, a physical system can be described by nth order differential equations. We have seen many examples of mechanical system, hydraulic system, electrical system, pneumatic system in our earlier classes, and we have seen that we can describe the physical system with the help of a nth order differential equation. Now, utilizing a set of variables which we call as state variable, we can obtain a set of first order differential equations. Okay. And we can group these first order differential equations using a compact matrix notation, and this is what is called as the state variable model. Now, as I was telling you, the time domain state variable model lends itself readily to computer solution and analysis. It makes our analysis simpler, and this time domain techniques can be utilized for say non-linear system, time varying system, as well as multivariable system. So, as I told you, the modern control system is based on the concept of states, and it utilizes this concept of the state variable approach. So, before we proceed, let us see some background. What do you mean by state actually? So, the state of a dynamic system is the smallest set of variables, and the thing about these variable is that if we know these variables say at some time t is equal to t0, and we know about the input say for a time t equal to and greater than 0 completely, then we can determine the behavior of the system for any time t equal to as well as greater than t0. Okay. So, this is how we define the state, and the state variables, these are basically the variables making the small set of variables that determines the state of the dynamic system. So, basically these are the set of variables that determine the state of the dynamic systems. Okay. And if at least say n variables say x1, x2, xn are needed to completely describe the behavior of a dynamic system, then such n variables are the set of state variables. And remember one thing, these state variables need not be physically measurable or observable quantities, but if you are trying to make certain feedback system, then of course you need to know these you need to have these state variables are measurable, then only you can use it in the feedback system. Okay. So, if feedback is needed for some system, then it should be easily measurable, the state variable. So, when we decide about the state variable, these factors has to be kept in mind. Now, state vectors, if I stack these variables in the form of a vector or say as a component of the vector, then what we call it as the state vector. Okay. That is, the n state variable can be considered as the n component of a vector x. Okay. And this vector is called the state vector. Thus, the state vector determines uniquely the system state x t for any time t greater than or equal to t0, once the state of at the time t is equal to t0 is given, and of course you know the input for time t greater than or equal to t0. Now, state space, basically what we call it, it is a basically mathematical concept, that is it is a n dimensional space whose coordinate axis consists of say x1, x2, xn, and this is called the state space, and any state can be represented by a point in the state space. Now, let us look at the state space equation. Now, in a state space modeling, basically we come across three types of variables. Okay. And these variables are the input variable, the output variable, and the state variables. And state space representation for a system is not unique. Okay. So, you can have the different way of representation of the state space model for a system, but the number of state variable are going to be same. The number of state variables are the same for any of the different state space representation. So, you may have a different way of representing the system, but number of state variables has to be same. And the dynamic system must involve elements that remember the values of the input for t greater than or equal to t1. So, the question is that how to select the state variable, or what should be the state variable. So, if you remember or if you recall, when we were discussing about the bond graph modeling, then I talked about how do we get the equations, state equations from the bond graph model, and that time if you remember I said that the equations derived from bond graph model are in the state space form, that is first order differential equations, and the states were basically the absorbed causes, and those absorbed causes were integration of the causes. Okay. So, the its concept is basically the same here also, that integrators in a continuous time control system serves as a memory device, and the output of these integrator can be considered as the variable that defines the internal state of the dynamic system. Okay. So, these are basically the integrators, okay, which basically facilitate us in selection of the state variable. Okay. So, the output of the integrators works as a state variable, okay, and the number of state variable to completely define a dynamic system is equal to the number of integrators involved in the system. So, let a MIMO, that is multi input multi output system, involves say n integrators. Then suppose there are R inputs, we have say U1T, U2T, URT, and we have say M outputs, say Y1T, Y2T, YMT, and suppose there are n state variables, say x1t, x2, xn, okay, and these state variable, as I said, these are the output of integration. Okay. So, the concept of selection of a state variable is same, whether it is bond graph modeling or whether this is the general way of modeling which we are talking about. Okay. So, it is basically the integration of that is output of integration, which is the state variable. Okay. So, the we can consider the system can be described as say x1 x1 derivative t is equal to f1, and this is function of all the states, say x1, x2, xn, all the inputs u1, u2, ur, and say time. Okay. So, likewise I can describe the system say by x2 dot, here again f2, which is a function of all the states, all the inputs and time, and likewise say xn derivative, this is function of all the inputs, all the states and all the inputs and time. And we can describe output of the system, okay, say y1t, y2t, ymt, there are m outputs as I told you. Then these outputs are function of say g1, that is g1, these are function of all the states, all the inputs and time. Okay. Similarly, y2 is function of all the states, all the inputs and time. Similarly, ym is function of all the states, all the inputs and time. Now, if we define say ut as this u1, u2, ur, that is input vector, okay, and xt, say these are the state vector x1t, x2, xnt, and say fxut, if I define like this, okay, f1 which is a function of all states, all inputs, time, likewise f2 and fn if I am able to define. Then for say output vector I define as y1, y2, ym, and say this g which is a function of states, input and time, if I define like this g1, g2, gm, all the states, all the inputs and time. So, if I do that, then I can write the state equation x dot t is equal to f x u t, okay, and I can write the output equation as y t is equal to g x u t. So, this is basically the compact form representation of the state equation and the output equation. Okay. Now, if these f and g involve time explicitly, then the system is called a time varying system. Okay. And if we are able to linearize these equation about the operating states, then the linearized state equation and output equation can be written as this way. Okay. So, here the state equation x derivative t is written as say a t into xt plus b t into u t, and y t is written as c t xt plus d t u t. Now, here what are these A, B, C, D? These matrices are very important. So, the A matrix we call it as the state matrix, okay, and this matrix is being multiplied by state vector, we call it as the state matrix. The BT matrix is being multiplied with input vector, so we call this as the input matrix. The CT matrix is multiplied with XT vector, so we call it as the output matrix, and the DT matrix is being multiplied with the input vector UT, so that we call it as the direct transmission matrix. Here this CT is multiplied with the XT, that is the state vector. Now, if the function f and g do not involve time t, okay, explicitly, then the system is called a time invariant system, okay, and in that case the state equation and output equation can be written as, that is, this A, B, C and D, they are not going to be the function of time, okay. So, I can write this as A x t plus B u t and y t is C x t plus d u t, and these are the state and output equation for a linear time invariant system, okay. So, remember these two equations are the very popular equations, that is state equation is A x t plus B u t and the output equation y is C x t plus d u t. We can take an example to illustrate the concept of derivation of the state space equation, okay. I will take again the very well known case of the spring mass damper system. You can take in fact any system. We have seen the several examples during our course of electrical, hydraulic, pneumatic, thermal, any system can be taken, but here I am just illustrating this concept of derivation of state space equation of by taking this spring mass damper system, okay. So, in this system we have a mass, say m, there is a spring and there is a damper, say this is subjected to certain input ut and say yt is the output, okay. So, we have seen the conventional way the system equation is given as this one, and of course, all of us know how we did that, okay. We drew the free body diagram for it and we found out all the unbalanced forces which are going to act on this body, and then we equated those unbalanced forces to mass into acceleration and we got this equation, okay. So, this m d square y by dt square plus c dx by dy by dt plus ky is equal to u. So, this equation can be written, the system equation can be written like this, m y double dot plus c y dot plus k y is equal to u. Now, see, it is a second order system because we have the highest order here is the 2. Now, it means that this system will involve the two integrators, okay, because it is a second order system. So, if there are two integrators, it means that there are going to be two state variables in this case, alright, and let these state variables be say x1t and x2t, okay. So, I am taking these two state variables x1t and x2t, and let me define this x1t as yt and x2t as y derivative t, okay. Then if you look at it, then what happens, as I said, we are interested in finding out the state space form. So, x1t I am writing as yt and x2t I am writing as y derivative t. Fine. So, what is my x1 derivative? So, if I take x1 derivative here, so this will be basically y derivative, and y derivative we are already writing it as x2. So, it is x2. Okay, basically right hand side I want to write in terms of states, okay, and my states are x1 and x2. So, that is why I am doing this manipulation, okay, and my system equation as I have shown you is my double dot plus cy dot plus ky is equal to u. Okay. So, from here I can write y double dot is equal to minus say c by m y dot minus k by m y plus u by m. So, I have the y double dot here, and y double dot is basically what it is going to be x2 dot. So, I have x2 dot is equal to this y double dot, okay, and y double dot is this one. So, this is minus c by m, and this y dot we have already taken as x2. So, I just write minus c by m x2 minus k by m. What is my y? Y I am writing as x1 plus this is u by m. Okay. So, it is this equation basically which we get x1 dot is equal to x2 and x2 dot is equal to minus k by m x1 minus c by m x2 plus 1 by m u. Okay. And what is my output equation? Output I am interested in knowing y. Okay. My output is y, and what is y here? This y is equal to x1. So, this is my output equation. Okay. So, this is my output equation. Fine. Now, what I can write it? I can write this equation in the vector matrix form, and remember I want to put my expression in this form. So, that I can do using these two equations, that is I write the derivative of the states x1 dot x2 dot derivative is equal to my A matrix here, plus I want to write my state vector. So, it is x1 x2 plus I will have the B matrix, I do not know what it is, I have to find out, plus my u. Okay. So, from here you see that x1 dot is equal to x2. So, I can just write 0 and 1 here. So, when this gets multiplied I get x1 dot is equal to x2, and I put 0 here. Similarly, x2 dot is say minus k by m x1. So, I write here minus k by m, this is going to be multiplied with x1. So, minus k by m x1 minus c by m x2 and then plus 1 by m into u. So, this is my 1 by m into u. So, this is my this equation, that is equation in this form. Okay. Similarly, I can write the output equation, that is y, and remember this output equation has to be written in this form, that is c x t. So, there is a c and there has to be x t, that is state vector. So, x1 x2 here, and my y is x1. So, this has to be 1 and this has to be 0, and of course, I do not have anything else here. So, my d is going to be 0 here, and of course, I will have the u. So, this is how I can express my system equation in the state space form. Okay. So, I hope you have understood it. Okay. So, we have the vector matrix form state equation, and this is my state output equation. So, from here, from these equation, I can identify what is my A matrix, what is my B matrix, and what is my C and D matrix. Okay. So, here you see that this basically this term which is this matrix which is being multiplied with a state vector here, this is your A matrix, this matrix is basically your B matrix, and this matrix is your C matrix, and this matrix is your D matrix. Okay. So, this way we can identify the A, B, C and D matrices. Okay. Now, another very important concept is that how can we derive the transfer function from the state equation. So, the state equation which we have seen here, from these state equation we can derive the transfer function. Okay. And as you know that once you have the transfer function, or when you have moved into the complex domain, again there are many number of control tools available to analyze and see the behavior of your system. So, the transfer function of single input single output or SISO system can be obtained from the state space equation. So, we have these state equation, and this is our output equation. Okay. So, I have explained all the associated terms A, B and C and D, where here YT is the single output and UT is the single input. Now, if I take the Laplace, if I take the Laplace transform for my this state space equation, okay, so this first derivative I can write as Sxs minus x0, okay, and this is equal to Axs plus Bus. You know, we use the capital letter representation to represent the parameters in the Laplace domain. Okay, here S basically indicate that these are in the Laplace domain. Similarly, I can take the Laplace for this one, that is Ys is C Xs plus Dus. So, this way I can do that. And when we are talking about transfer function, so as I told you at the beginning of the transfer function lecture, that this transfer function is valid only if our transfer function can be derived only if we assume that all the initial conditions are 0. Okay. So, this x0 I have to take it as 0. So, what I get Sxs, and I take this to the left hand side here. So, minus Axs is equal to Bus. Okay. And of course, I have my Ys is equal to Cxs plus Dus. Now, I can further simplify this equation. This I can write, I take Xs outside. So, this is Si minus A, where I is the identity matrix, Xs is equal to Bus. Now, I can do the pre-multiplication both the sides by the inverse of Si minus A here. So, this inverse mine into this one will be giving me the identity matrix. So, I get Xs is equal to Si minus A inverse into Bus, and you know our Ys relation is Cxs plus Dus, or I can have Ys is equal to C, this Xs I can substitute from here, that is Si minus A inverse into Bus plus Dus, or this Ys I can take Us outside from here. So, I have this C Si minus A inverse into B plus d, this us is outside here, and now I can define the ratio between the output and the input, that is ys my divided by us, of course with the initial condition of 0 value, initial value. So, this will be giving me C, and this complete term I will be getting, and I can just explain this concept using the same problem which we have considered here. So, again the same spring mass damper system, and this is my the dynamic equation. One way of doing it is that I can take the Laplace transform directly here, okay, and assume the initial condition to be 0, and I can find out the transfer function. The other way through state space approach is that these are my state equation and this is my output equation. So, I can find out the transfer function ys by us as the expression which we have just derived, and then I can substitute the value of C, value of A, value of B, and of course D is 0 here. So, if I put these values here and I work it out, take the inverse and do the multiplication, I get this equation, and this is the very popular form of the transfer function for a second order system, that is 1 by ms square plus cs plus k. Okay. So, with this I will wind up this lecture, and if you want to have further reading, if you want to see many more examples, please refer K. Ogata Modern Control Engineering textbook. Thank you.